and then share the screen. Okay. I pay a lot of attention by my Apple Pencil now because of this accident last time. Okay, so there is not much time left, so somehow I want to come to a good end. We are discussing the Noether normalization lemma, and then it will be the Hilbert-Nullstellensatz. Okay, I already stated the Noether normalization lemma, so actually I wanted to prepare it, but right, let me do the following. Oh my gosh. I want to copy it. Then insert it here. Okay, it's on the second page, but it doesn't matter. Okay, so can you see it? The Noether normalization lemma. So what does it say? We have a finally generated K algebra over a field. I'm here. And then it says it's possible to find elements in A that are algebraically independent over K with the property that, okay, when you look at the algebra generated over K by these elements, this is structurally a polynomial ring because the x1 up to x are algebraically independent. But then the statement is the extension from this polynomial ring to A is an integral extension, an integral ring extension. Okay, this is always possible. And we also said if K is an infinite field and my algebra is generated by elements A1 up to AN, it's possible to choose this Xi just as linear combinations of the generators. Okay, that's an important result. Now let's go for let's prove it. There is a very simple lemma. It's not even a lemma. I mean, it's very simple, but let me write it. So let's assume I have a polynomial f over my field K of degree d. Okay. And the point is I would like to turn this, right, what do I want? I distinguish one variable, say xn, and I would like to have that f viewed as a polynomial in xn is monic of degree d, because this is the condition I need for these integral extensions. And the lemma says one can always achieve this by a simple linear transformation. Okay, so I need more notation. Let f sub d be the homogeneous part. Okay, let be homogeneous part of degree d. Okay. Okay, then what I do? Okay, I take some feed elements, lambda 1 up to lambda d minus 1. No, actually n minus 1, sorry. Lambda n minus 1. They are in the field. Okay, and then I make a transformation. So instead of x1, I put x1 plus lambda 1 xn, and so on. I always add, okay, here, I add a multiple of xn. Xn, sorry. What do I do? So, and the last I leave unchanged. Okay. This is the transformation. So xn is the distinguished variable unchanged. Maybe it should have a different name. And to the other variables, I add a multiple of the distinguished variable, okay, with some constant factor, some lambda. And the point is now, if I expand this, okay, I view it as a polynomial in xn, then it must have this form. Some constant, xn to the d, plus some lower order terms, so which I can write this way. The coefficients here, they are now polynomials in x1 up to xn minus 1. And then here comes xn to the I goes from 0 to d minus 1. Okay. So this is, I mean, everything I wrote so far, I think is clear. So the coefficients are polynomials in the variables x1 up to xi minus 1. And the only interesting part is about these coefficients, because I want this coefficient to be non-zero. Okay. And the statement is about this coefficient. It says, how do I get this coefficient? Well, I get it. I take the homogeneous part of degree d of my polynomial, the ft, and I plug in the lambdas. So lambda 1 up to lambda m minus 1, and the last is 1. So the statement, the lemma is about how to get this coefficient. Okay, and what is the proof? The proof is a one-liner. Okay, say in this representation star that exists, I just make a substitution. So I send the variables, all the variables go to 0 except the distinguished one, except the last one, the xn, which I send to 1. The others go to 0. Right, and then what do I get? Well, you see, this goes to 1. So there is the constant c, but all of these contributions here, they go to 0. Because, right. What do I, okay, so maybe let me write. It's not quite correct. Sorry, I'm going to. Okay, so this condition here, okay, I have, but now I think, how does it look like for the homogeneous part of degree d? Okay, so okay. Okay, so what it will be, it will have this contribution. And the remaining contributions, they are homogeneous. So these are terms of degree less than d, terms of degree less than d in xn. And the point is, if I focus here on the homogeneous part, then all of these contributions will be homogeneous of degree d, right? So if this, let's look here, for instance, but if here I have a degree I in xn, then these coefficients should have degree d minus I in the remaining variables. Okay, so now if I make the substitution, as I said before, okay, what do I get? Then I get, so everything vanishes except the constant c. So I have ft. Here I put the lambdas, comma 1. This is c. And all the other terms, they disappear. Sorry for messing up this, but it's an easy argument. Okay. So actually, this is a trick that is done very often in the theory, in practice. You have a polynomial. You want to make sure it's monic with respect to a certain variable. Then you just make such a transformation, maybe a generic one, and then you achieve this. Okay, so this is this lemma. Now let's go to the proof of the Noether normalization lemma. So proof of Noether normalization lemma. Okay. So okay. So I only prove it in the case where the field is infinite. If the field is finite, the theorem is still true, but the proof is a little different. Okay, so let's not bother with that. So I assume A is generated by A1 up to AN. Okay, the assumption I have a finally generated K algebra, so there are such generators. Now let's reason the following way. I mean, in principle, it's an inductive proof, but I don't want to do the formal induction, but you will understand. So let's say, as a happy coincidence, these generators are algebraically independent. Okay, assume that. Then I'm done. Then I can just take, I mean, R will be N, and the generators that I'm looking for are AI. Okay, then I have the X A1 up to AN, they are algebraic independent, and everything is good. They generate the whole algebra. So nothing is, this is the case where nothing is to do. Otherwise, usually these generators are dependent algebraically. So there exists a polynomial relation. So it means there is a polynomial f, which is not constant. So say in variables t1 up to tn, it's not a constant polynomial such that when I plug in the generators, I get 0. So this is a polynomial relation. Okay. So, but because I want an integral ring extension in the normalization lemma, I want to make sure that this f is monic somehow. And now for this, we use this lemma from before. Now okay, let lambda 1 up to lambda n minus 1 be field elements such that this constant from the lemma, I write it again, is non-zero. Okay, where d is the degree of f. Okay, so exists since k is infinite. So I have my f, okay, f has degree at least 1. So ft, this homogeneous part, is a non-zero polynomial. Now, if you have a non-zero polynomial, I mean, as a formal expression, you can, and you are over an infinite field, you can always find points where the polynomial does not vanish. So this is false over finite fields, but over infinite fields, it's okay. And now why can I pick here the 1 here? This is just because of homogeneity, easy to check. So I have this, good. Then, okay, by scaling, I can just assume that this constant is 1. Okay, I divide by c. Okay, so let's simplify the notation. C equals 1. So, okay, right. Now I will move to different generators. So I call them AI twiddle. So what I do, I subtract from AI lambda I times AN. Okay, this I do for I up to n minus 1. So the first n minus 1 generators will be replaced. So using the lemma, okay, now let's see how our relation changes. So I have f of the a's equals 0. This is my polynomial relation. Now let's see how does it look like with the transformed generators. So now that's an easy calculation. Now instead of A1, I can write A1 twiddle plus lambda 1 AN and so on. Okay, the AN unchanged. So now I use the lemma and it tells me there is this constant one, okay, but it's okay, 1 times this plus this lower order stuff. And here I have to plug in this twiddle stuff. So, okay. So there is no magic here. Now you see we have this polynomial relation. This is 0. But the nice thing is it's monic. Okay. So I see now that AN is integral over the, okay, integral over the subalgebra generated by the first n-1 generators, these twiddle ones. It's integral over this. Okay, good. So now, okay, we could go on like that. So, okay, I don't want to do induction proof. I just tells you like a story. Now you look at these things. If they are algebraic independent, we are done. Okay, then I can say my R will be m-1. This is an R. And take xi is ai twiddle. Okay, I have algebraic independent. And the extension from here to the algebra is an integral extension because, right, I adjoin one element, namely the an, and this is integral. And if I adjoin an integral element, we proved I get an integral extension. Okay, and otherwise I just proceed, inductively. Otherwise, proceed or continue procedure. Okay, okay. So you start now with this. You find the relation, okay, and then you make the transformation, etc., etc., etc. So I think one could write it in a more formal way, but actually I like this way of proving it. It shows that this is really a very, very simple thing. Okay, very simple. Okay, questions on that? Okay, good. So, right. So now let's move to the Hilbert-Nullstellensatz. I think it was already there in the exercises. So in the following, assume that the K is algebraically closed. Okay, so for instance, think of the complex numbers. Okay. So there is over the complex numbers, or more generally over an algebraically closed fields, there is this fundamental theorem of algebra. Well, what does it say? It says that any non-constant complex polynomial has a complex zero. And this is the definition of algebraically closed field. So, but the question, this is for polynomials in one variable. But what happens if you have several variables? Okay, so you have a whole collection of polynomials and you want to know, is there a common solution? Is there some criterion for that? Okay, it's like, think of linear algebra. You have a system of linear equations. There are conditions depending on rank and so on. And here there is also a condition, and this is the so-called Nullstellensatz, or the weak form. I mean, all of the work is in this weak form. Weak form of Hilbert's Nullstellensatz. Nullstellensatz. Okay, let me abbreviate it. Okay, it's funny in the US, in the Anglo-Saxon countries, the way they write Nullstellensatz, usually orthography is a bit wrong. Nullstellensatz. Okay. So what is it? I have a list of polynomials, f1 up to fs over k in the variables t1 up to tn. Okay. So I have polynomials. Now they generate an ideal. And I assume this ideal is proper. So let be polynomials generating a proper ideal. So this means, so this ideal doesn't contain 1. So it means it's not possible to write 1 as a linear combination of the given polynomials. So let me write in negative. There is no way to write 1 as a linear combination of the fi. Okay. And the coefficients are polynomials. No way. Okay, I mean, it's not possible. Okay, so this expresses 1 is not in this ideal. Okay. So, and the statement is then there is a common 0. There is some small x in k to the n such that for all, okay, all these polynomials vanish there. Yes, many. So that's the Nullstellensatz. That's a very important result. Okay. So maybe you can even phrase it as an if and only if condition. Just assume that, let's assume we would have such a, we would have such a relation. Okay, so if we have this, then we directly see it's impossible that the fi have a common 0. Because take any x, plug it in here. Okay, if x is a 0 of all the fi, then here I will get, this will all be 0. So I will have 0 here, but here there is 1. So this is impossible. So clearly, if I have such a relation, it excludes that the system has a solution. But the theorem says, well, okay, but it's enough. I mean, if we know there is no such solution, there exists. There is no such linear combination, that exists a solution. Okay, so proof. Right, there are different proofs. So as I say, this theorem is very important, and it's by no way, you will see the proof. The proof will be short, but it will not be a proof that tells you how to find the x. It will not be constructive. So the original proof, I think, going back to Hilbert and so, it was actually constructive and it used the resultants. Okay, right. Okay, whenever you want to have quantitative information, so for instance, you know, these polynomials here have the degree at most d, say, okay? Then you wonder, how large should the degree of these coefficient polynomials be? So nowadays we know exactly what it is, but these are results that, okay, they are not 100 years old, maybe they are just 25 years old and so on. They are not so easy. Okay, good. Now proof of the Hilbert-Nullstellensatz. So it's not constructive. So okay, whenever something is not constructive, it deals with a maximal ideal. Okay, so let M be a maximal ideal. Be a maximal ideal. Okay, of my polynomial ring containing all the f's such that, so I can say such that, okay, my ideal in the polynomial ring, which I assume is proper, is contained in M. Okay, that was the Zorn lemma trick. So we have a maximal ideal. Then what we do with it, we look at the factor ring. Now this must be a field. Okay, I call it A. Doesn't sound like a field, but this is a field. Because I divide by a maximal ideal. That is a field. And now A is generated by the residue classes of the variables. I write them with bars. Okay. So where Ti bar is just stands for Ti mod M. Okay. So good. Now comes the Noether normalization lemma. Okay. So the first step was not constructive, but the Noether normalization lemma is quite constructive. Noether normalization lemma, if you think of the proof, it tells us there are such algebraically independent polynomials. I write them H1 bar up to HR bar in A, algebraic independent over K, such that the extension, so from this polynomial ring, okay, this to A is integral. Integral ring extension. So clearly I write HI bar because it comes from a polynomial HI. Okay, so what's the point now? But this is a field, I said. Now we had the result saying, if you have such an integral extension and here there is a field, then this must be a field as well. Okay, so must be field as well. So that was the proposition. Nadia McDonald's is 5.7. We proved that. Okay. But that's really strange. We have here, this is a polynomial ring in R variables, and this is a field. The only way this can happen if R equals 0. There are no variables. Otherwise, it's impossible. So must have R equals 0. Okay. Good. So what we get actually, so what I have, this extension, this integral extension, okay, it goes from K to A. So it's an algebraic field extension. Okay, because K is a field, A is a field. One is the subring of the other. And integral extension means algebraic because now I deal with fields. So this is algebraic. But K is assumed to be algebraically closed. So K must be A because K is algebraically closed. Okay. Now I see that this A is just this is the ground field. Okay. Right. So that there are now elements, there are x1 up to xn in K such that, okay, xi is congruent to Ti mod M. So you see all these Ti bar here. I mean, they are in A, but A equals K. So they are congruent to field elements. Okay, and this is what we needed. Now we have. Now, let's see. Let me write it. It's basically one line. fi. I plug in this x1 up to xn. Okay, but this is the same of it. If I go for congruence mod M, the maximal ideal, I can put here as well the t's. Okay, this is, let me say, mod M. This is a congruence mod M. But the fi, when I plug in the t's, okay, this is fi. This lies in my maximal ideal. So this is congruent to 0. Okay, the maximal ideal contained all the fi. And that's what I wanted to show. So now I see this thing congruent 0 mod M, so it's in the maximal ideal, but it's also in K. Because fi is a polynomial with coefficients is K, I plug in elements in K, it's in K, but this is 0. So I see for all I. So can I do this for all I? Now I see this x1 up to xn, these are common zeros. That's the proof. Very short and elegant. It's probably the shortest proof that exists. Let's say it's always a bit critical. I mean, the only disadvantage is this. Okay, doesn't tell you a lot about how to find the zeros, because how do you, what is maximal ideal? This is just exists. Okay, but for the existence, it's good. It's elegant. Okay, so the proof also shows, let me record an important corollary. So proof shows for corollary. So it's about the maximal ideas in the polynomial ring. So I write again, let K be algebraically closed. That's important. So the maximal ideals of the polynomial ring are of the form. I can write them M sub x. This consists of those polynomials that vanish at x. So these are vanishing ideals of points. For x in k to the n. I think we had it before that if you have such an ideal, then it's very easy to see, the polynomial ring modulo this mx is isomorphic to k. So the factor ring is a field, so mx must be maximal. The point is here really that every maximal ideal looks like that. So this follows from the proof. And the assumption that the field is algebraically closed is important. So little remark, this is false, totally false. When you take, for instance, you take the real numbers. Here is an example. Here is the standard example is t squared plus 1. Just a polynomial in one variable, t squared plus 1. This is a maximal ideal of this polynomial ring. Since let's check. Let's see, I look at the factor ring. And this, if you think about it, or anybody knows what is this ring? It has another name. It's very well known.
It's C.
It's C. It's the complex numbers, right? That's a field. But as we all know, this polynomial has no zero, has no real zero. So the Nullstellensatz is great, but if you are interested in real numbers, it's not very useful. Actually, it's false. But over complex numbers is good. Right, and there is now this standard story with the Rabinovich trick. I think it was in the exercises, was it? Or somehow I have the impression I should do it. It's so important. Also, a repetition cannot harm. So now this is the Nullstellensatz itself. It's not the weak form. What does it say? I say again, K algebraically closed, because that's needed. Then I have polynomials f1 up to fs as before, and the further polynomial f, several variables. Okay. And what is the condition? I want to vanish. So the f1 up to fs, they have a zero set, the set of common solutions. And I want f to vanish on that. So I can write it explicitly the following way for all x in k to the n. If x is a zero of these s polynomials, then f of x equals 0. Okay, so this is the f vanishes on the zero set of those. And the statement is, okay, if this is the case, then f is in the radical generated by f1 up to fs. So this means, concretely, there is some exponent e, such that f to the e's power is in the ideal generated by f1 up to fs. Okay, that is, f is in the radical. So how did I write radical? I think with the root sign. Okay, write it this way, radical. So that's the, also this is so important that it maybe deserves a colored box. Okay. So that's the Nullstellensatz. Now the Nullstellensatz, once you have the weak form, the proof of this is extremely simple. And everybody knows it is a so-called Rabinovich trick. Okay, I'm quite sure that it was known before Rabinovich, like all these things, but you know, it's good to have a name, the Rabinovich trick. So we reduce to the big Nullstellensatz as follows. I take a further variable, let y be further variable. Okay. So then I look at these polynomials. I have my polynomials, maybe suggestive notation. I write the arguments. Okay, t is now a shorthand for t1 up to tn. And I add this polynomial 1 minus f of t times y. Okay, now I look at these polynomials. I have one more polynomial, one more variable, and I claim it cannot have a common solution. It doesn't have common zero. Okay, nowhere. Let's say in km plus 1. It's not possible. Typo. Why? I mean, assume there was a solution, plug it in, then, right, let's see. You take your x here. Here is x. Then all of these f1x up to fsx are 0. So, okay, they are 0, okay? But then this says f of x should be 0 as well. So here I would also have 0. So then here I get 1, okay? It's impossible to get here a 0. You see? Because of, if here is 0, here must be 0, so here I have 1. Okay, that's good. Right. But then now I use the weak Nullstellensatz. The weak Nullstellensatz says, okay, I don't have a common 0, so I can find a linear combination of the one. So there are coefficient polynomials H0, H1 to HS, and they are okay in all the variables I have in the T's and the Y. And one is now H0 times, here comes 1 minus F. Now I don't write the T anymore because it's a bit annoying. Okay, I write it. So this is a linear combination of 1. Okay, now I have to get rid of the Y. How do I do it? Well, I just substitute. I send Y to 1 over F. Okay, when I do this, then this contribution will be killed. This disappears. Disadvantage is I leave the polynomial ring. Okay, 1 over F. Okay, so I have to restore this somehow. So let me write. So the first one goes away. Then I have this sum. Let me write this way. On the one hand, I have the t's t1 up to tn, and the y's is now 1 over f. And I have f I of t. Now I just have to multiply with a sufficiently high power of f, so I get polynomials again. So E, let this be the maximum over the degrees of hi. Then if I multiply with f to the e, I have this. Now these things, now it's easy to check that these expressions here, they are polynomials. So this is a polynomial. Okay, and then what I see, I think it fits this line f to the e, so is in the ideal generated by f1 up to fs. That's the proof. So you see this reduction is very constructive, right? Very useful in a way. Okay. Questions? Okay, probably you could wake me up in the middle of the night and I could just do it. I know these things so well. Okay, so now, so this was the work. The weak Nullstellensatz, there's the work. The full Nullstellensatz is just a Rabinowitz reduction. But now let's spend a little time in rephrasing what we have. Okay, because the formulation of the Nullstellensatz, when you see it for the first time, it may look a bit complicated. Okay, but what we can do, we introduce some concepts, some notation, and then it becomes, in a way, nicer to understand what's going on. So now we actually only reformulate. There will be no addition in contents, but it's useful to do it. So now I think this was in the exercises, but this is like a recap of what was in the exercises. So I defined a zero set of an ideal. Sometimes people write Z of A, and now I write V, I don't know, vanishing of ideal A in the polynomial ring. S, okay, what is it? It's the collection of all those points in K to the N, such that all F in my ideal vanish there. So set of common zeros of all the polynomials, the ideal, okay. Okay, it's clear if you say you are just interested in two polynomials, then the zero set of these two polynomials clearly will be the same as the zero set of the ideal generated by the two polynomials. That's why we talk about ideals, okay. Okay, and the other object of interest is the vanishing ideal. Vanishing ideal, let me, I of E of subset. This E is a subset of K to the N. The vanishing ideal I of E is defined as collection of those polynomials, okay, such that they vanish as functions on E. So for every x in E, f of x is 0. It's the vanishing ideal. Okay, it's the vanishing ideal. Okay, so okay, a remark. So this was in the exercise. Let me just recall it. Okay, exercise. I think it was in the exercise. The vanishing ideal of E is always a radical ideal. Okay. Okay, the second thing, right, actually I said it, but I can write it, but it's quite important, so let me write it. If A is generated by the polynomials f1 up to fs, then the vanishing ideal of A is just a common zero set of these polynomials. It's exactly what I said, but let me write it anyway. So even if you are interested in finite collection of polynomials, it's very natural to go to the ideals. Now we have these two processes. Let's say I have a set E. I take vanishing ideal and then zero set. And then it's trivial to check that this always contains E. If you don't see it immediately, don't worry. It can be confusing, but it's completely trivial. Same if I have an ideal in the polynomial ring. Now take zero set, vanishing ideal, I get something that contains A. This is also trivial. You check for yourself. The question is, when do I get equality in 3 and 4? Okay, then there is the following definition. A subset E of k to the n is called algebraic if it is a zero set. Okay, if it is of the form zero set of an ideal. Okay, for some ideal A in the polynomial ring. These are the algebraic sets. Zero sets of ideals. Okay. Okay, so these are just algebraic sets are just solution sets of systems of algebraic equations. Okay, and then there is another. Okay, I have another remark saying that if E is algebraic, then in this inclusion, actually we have equality. Let me also put here exercise. I don't have much time left, and I think it was in the exercise, and if not, it's very easy. There's nothing deep about it. Okay, and now comes, so where is the meat? Okay, so where is the non-trivial thing is in this corollary, and this is a reformulation of Nullstellensatz. So for any ideal A of the polynomial ring, K must be algebraically closed. We have the following. Ideal, I take zero set, and then vanishing ideal. So let's see. Here, I said it contains A. Yeah. But in general, it's not equal to A. And it turns out this is exactly the radical of A. It's the radical of A. So this is a reformulation of Nullstellensatz. Okay, so the proof said, I said this inclusion was clear and the other is just a Nullstellensatz. Think about it. It's exactly that. I said it. You see, this is exactly, where was it? here. I mean, you have to think about it with yourself, but here, the statement, there is an exponent such f to the e is here. So f is in the radical. This is exactly it. If you don't see it, please ask me next time. But I think, yeah, that's what it is.
Just one short question. We have to argue that this ideal A can be generated by finitely many polynomials.
A very good point. Very good point. Very good point. Right.
I mean, we showed it already with Bruckner basis, I think, but we have to say it, I think.
You got me. This is true. You found a gap in my argument. This is true. Because the Nullstellensatz, as I formulated, let's see, was for an ideal, finally generated ideal. But there are two answers. One answer is, suppose I had, okay, an infinite number of f's. The proof would still work. I mean, the weak Nullstellensatz, nothing would change. Because you see, even if here you have an infinite number of generators, if the ideal is proper, you can put it in a maximal ideal. One thing. Second answer is, we know already that polynomial rings over fields are Noetherian in a way, meaning that every ideal is finally generated. So this we prove with the help of Grabner basis. So we are on the safe side, but you are right. Okay, this is a very sharp comment. You're right. Okay, so maybe I should write it, use, okay, and use that. Okay, I in the Noetherian. Okay, we'll discuss this. Okay, next week anyway, Noetherian. Every ideal is finally generated. So, okay, and this leads then to really nice correspondence. I can also put it as a corollary. If we have space here, so have inclusion preserving bijections. So I think this is so important. It should be, I put it on a different board if I can. Okay, worked. So on the one hand, we have the collection of algebraic subsets. Okay, to the n. On the other hand, we have the radical ideals. The polynomial ring. Okay, and then we have maps going in both directions. On the one hand, I have an algebraic subset. I map it to the vanishing ideal. Or I have an ideal. I map it to the zero set. And these bijections are inverse to each other. Okay. Okay. Inverse to each other. Inverse to each other. So, right. So the point is really, you see here, if A is a radical ideal, I can write here A. So I see, do first V, then do I get back A. And this I know anyway. Okay, so this is a rephrasing of that. Okay, and then maybe one last, okay. Okay, I have to say it. So one can define the so-called Zariski topology. I think it was the exercises one defines the Zariski topology on K to the N. by declaring these algebraic sets to be the closed sets. By declaring the BA to be the closed sets. Okay, and then it needs a little bit of thinking to show that the axioms are satisfied. So we get the topological space. It's quite a strange one because it's not Hausdorff, but it's even nevertheless, it's useful. So that's the Zariski topology. Okay, and then I don't know whether, okay, I'm not sure exactly what Marco did in the exercises. So let me just write this. So this is irreducible, but I'm not sure whether it was defined. Do you remember? Anybody remembers whether irreducible was defined? Okay. Nobody remembers. So whatever, it has a definition, and it turns out that this is irreducible if and only A is a prime ideal. Okay, so maybe I don't enter this story because it will take time, but the point is really that yeah, it's very important in a way that to understand. So in commutative algebra, you have the polynomial ring, and then you look at the prime ideals of it, the spectrum. It doesn't have a geometric meaning a priori, but in fact, there is one, especially if the base field is an algebraically closed field. Then you have this correspondence. And then you see the prime ideals bijectively correspond to the so-called irreducible algebraic sets, which has an imminent algebraic meaning. Okay. So, and that's somehow the idea that geometric ideas here on this side can be transferred here. And then yeah. Why would people do that without this? But then people realized, okay, so if I work here, I kind of have a geometric idea, or at least I pretend I have one. And then they realized, oh, it even works if my field is not algebraically closed. It still works. So you this world, this is the algebraic world, while this is the geometric world. The algebraic world has its own existence, even if the field is not algebraically closed. Everything works. It's very pure and clean. That's commutative algebra. But if you really want to understand what's going on and where the ideas come from, I think you need to know about this correspondence. Okay. But my lecture focuses now on this algebraic thing, which, yeah. Okay. Comments on that or questions?
Just to be sure, you said the right-hand side also works if K is not algebraically closed, yes. But the correspondence only holds if K
the correspondence is not true anymore.
Yeah, okay.
But you can study the prime ideals, and I mean, all the results. I mean, okay, we didn't prove so many results, but let's, for instance, look at the Newton normalization lemma. You don't need algebraically closed. Or the going up theorem, you don't need that. I mean, almost never. I mean, this gives a lot of flexibility that you don't need to, yeah, things work in very, very general. Sometimes one has to worry about characteristic or whether some base field is finite and so, but it works in general.
Okay, thanks.
Good. So that's okay. So I was running a little bit. This is good because I'm running out of time. So now let's jump into the next topic. And the next topic, okay. This morning I prepared a little bit of shortening. Okay, next, this is now the chapter 6. Okay, we don't have the chapter 6. And this is on Noetherian rings or modules. Okay. Noetherian rings the module. So I want to do, this will be a very short chapter because there's not much in it. It's not difficult. I want to do this. And then I also want to talk about primary decomposition. More I cannot do in this lecture. I spent so much time with the Gröbner basis. Okay, what is this? Noetherian, named after Emmy Noether. She was the first to realize the importance of this concept. This is a finiteness condition. So let me give the definition. Okay, I have an A module M. Let M be an A module. Okay, we call M Noetherian. Noetherian. Okay. If, okay, there are various ways to characterize it. This is very traditional, and there are three conditions, they are equivalent. So if the following three equivalent conditions okay, and then we will verify that they are equivalent. So one is, okay, the chain condition. So every increasing chain of submodules becomes stationary. Chain of submodules. So you have submodules. So you start with N1, then you have N2, this containment, and so on, of submodules of M is stationary. And this means there is some index, say M, and after that index, there is no increase anymore. Okay, increase stops at some point. Okay, second condition. This is an abstract one, but it reminds a little bit of Zorn's lemma. Every non-empty set of submodules of M has a maximal element. Every non-empty set P of submodules of M has a maximal element. Meaning that there is a, okay, the element is a module that you cannot extend any further without leaving this P. Okay, strange condition, yes. And third condition is every submodule of N is finally generated. Okay, say, give it a name. Every submodule N of M is finally generated. Okay, so I don't know, maybe you have seen this. Who has seen this? Oh, okay.
Didn't we kind of discuss it in the second chapter?
In the exercise or?
No, in the chapter about Gröbner basis. Where we
oh, I did do it. Can I skip the proof?
I don't know. I think you can skip it, but you don't have to skip it.
Okay, what do you think? Can I skip it?
I don't know. Maybe is it like super similar to the proof with rings and ideas?
Yeah, it's all the same. So let me okay, because let me skip the proof. Okay, you try to give the proof. It's really simple. I mean, it's kind of abstract nonsense. I mean, you just think about sometimes. Okay, I would go this way. And sometimes if you don't see it, try to prove the contraposition. So equivalence, I want to leave it to you. And if there is a problem, tell me. I'm happy to explain to you, but it's really simple. It's not, yeah. I mean, really the achievement here of Noether was to realize that if we have this condition, we can prove so many things. very abstract. Okay, so and then there are a couple of properties. So this collection of Noetherian modules really behaves nicely. It's closed undertaking submodules, homomorphic images, and blah, blah, blah. So here is a proposition 6.3. That's really nice. It's formulated in terms of exact sequences. Why not? So I have a short exact sequence of A modules. B exact sequence of A modules. So let's call this map alpha and this beta. Then the statement is M is Noetherian if and only if M prime and M2 prime are Noetherian. Okay, so right. So for instance, I mean, as a corollary, we see, so what do we see? So if M is Noetherian, then M prime is Noetherian. So it means M prime is just a submodule. So it means you have a Noetherian module, go to a submodule, will be Noetherian again. Actually, this is trivial. I mean, just think of the characterization 3, okay? It's trivial. I mean, the other thing, also M2 prime is Noetherian, so it means homomorphic images of Noetherian modules will be Noetherian. Okay, it's also very, I mean, it's also very, very simple to see, actually. You could prove it for you. And there is maybe a little bit more interesting is this arrow back. But let me prove it. I cannot. Okay, I go to my notes. That's page 110. Then I will not mess it up. Okay, page 110. Good. Yeah. So here are my notes. So I try to give the proof in detail. Yeah. So let's do, this is the simpler direction. Okay, so M is Noetherian. So let's first show Noetherianity of M2 prime. There are now several options. I mean, I can work, you know, I have 3 equivalent conditions. So I think I use the condition 1 about stationarity. But that's a matter of taste. It doesn't really, it's not very important. So let's assume I have a chain of submodules of M2 prime. Okay. Submodules of M2 prime. So then actually this proof is in a way an automatic proof. I mean, what can you do? You just pull it back with the beta. Now I have a chain of submodules of M. Okay. Now I know, or my assumption is M is Noetherian. So there is some index, maybe N. And after that index, things become stationary. So I put here N, and then the next one, N plus 1, etc. Okay, become stationary. Now I just have to check that this also is true for the M2 primes. But now I just use beta is surjective. So I have here this equality. I apply beta, and I get this. So what I see, right. So I see M2 prime Noetherian. So Noetherian. Okay. So and the same game, okay, or similar game I can do for the M primes. So if I have a chain here, submodules of M prime. So what do? I just apply alpha. Okay, alpha is injective, so you may think of inclusion. So I have submodules of M. Now I use its Noetherian. So there is some index n, and after that index, it becomes stationary. Blah, blah, blah. Okay, now I use alpha is injective. So to see that, I must have this. The inclusion I have anyway, okay, but then I get the equality. So I see, so this is Noetherian. Okay, so I have proved the direction from left to right, and it was completely obvious. Okay, so the other implication, actually I don't need it, but let's do it. So it's not hard, but a little bit harder maybe, but not hard. So now I have a chain of submodules of M. I assume M prime, M2 prime are Noetherian. I want to prove M is Noetherian. I have submodules of M. I want to prove this is stationary. So, I mean, let's first take, so what do I do? Okay, I take inverse images of the Ln, or I map it with beta, and these are both ascending, these are, okay, chains. An ascending chain in M prime, and this is a chain in M2 prime. Okay, now I use that they are Noetherian. So there is some index n. Okay, I choose it big enough so it works for both chains, so that I have stationarity here. Same here. So now it only remains to check that the same index is good for the else. So the claim is now, actually, let me write the non-trivial inclusion. The ln is contained in ln plus 1 anyway, as we assume, but I claim this, meaning equality. Okay, and then, right. It's also true for bigger indices, and then I'm done. So let me check this. Okay. X, I take an X in ln plus 1. So what does this mean? No, it doesn't mean anything. What I want to do, I map it with beta. Okay. So I want to use, okay, I have X here. Beta of X is here. But this set coincides with this one. So this implies there must be a point, say, Y in Ln, such that beta of X equals beta of Y. Okay. So therefore, beta of X minus Y equals 0. Now I use my exactness. So X minus Y is in the kernel of beta, but the kernel of beta is the image of alpha because of exactness. So there exists Z such that X minus Y is alpha of Z. Okay, now, okay, so Z is in the inverse image of, I have to think. I want to write ln plus 1, what Y is that? Okay, yeah, because, right. Right, both. Okay, Y is in ln and X is in, why is that? Okay, now I got it. Because I also have this assumption that this is the inverse image of ln. This I also know. Okay, this is here. So they are equal. So my Z is here. Okay. And then, okay, I think then I'm done. X equals Y plus alpha Z. So it's in ln plus ln, which is ln. So the trick was actually, you see, to make very clear. Okay, maybe I was not very clear. Let me say this point again. Here, up here. This I know. Okay, I have ln and ln plus 1. And I know from the construction Z is in here with the bigger one, because Z is the difference. Okay, if I compute alpha Z is X minus Y. So X is in ln plus 1 and Y is in ln, so clearly in ln plus 1. So I have this. But then I use the equality here and have it. Okay, that's the proof. Okay. Right. Where are my notes? Okay, let me. Here, I found it. Too many papers. Okay, so corollary. So far, I realized it didn't have examples, but we'll have examples in a moment. This is the corollary 6.4 in Attia McDonald. So it says, if I have finitely many Noetherian modules and form a direct sum, it will be Noetherian. Noetherian. Direct sum will be Noetherian. So Noetherian is really a great property. It just, this property is inherited by almost all constructions. So the proof of that is just induction on N. Just let me, for the induction step. Okay. Induction. For the induction step, we just write this sequence, short exact sequence. Here I go up to N, then I project to the sum of the first M minus 1. This is surjective, and the kernel will be Mn. Is exact. Okay, then if I, for the induction step, okay, I know this is Noetherian and this is Noetherian, and then I apply my proposition. Apply, okay, apply proposition 363. Good. Okay, so these are Noetherian modules. Can somebody give me an example of a Noetherian module? Just one. I should have given examples, but
the polynomial ring in any number of variables.
How should I view it as a module then? It's a ring. So what do you now?
Oh,
yes, it's what you say is correct.
Yeah, as a module over the
correct.
base.
Very good.
Ring.
So now it's what like we talk to each other like abgesprochen, because this brings me exactly to the next definition. What is an Noetherian ring? So a ring is called Noetherian. Yeah. If it is so as an A module, so maybe the ring should have a name. A ring A is called Noetherian if it is so as an A module. Okay, this sounds a little bit indirect, but concretely, what are the submodules of A seen as a module? These are the ideals. So concretely, it means every ideal is finally generated. Every ideal of A is finitely generated. Or because of the equivalence from before, I could say every ascending chain of ideals is stationary. It's equivalent. Or every non-empty set of ideals of A has a maximal element. This is an Noetherian. So now here examples. Now it's very easy to have examples. You set the, okay, let's start with the easiest thing is any field. That is really trivial. Any field is Noetherian. Well, because the only ideals are 0 on the field. I mean, nothing can go wrong here. Then principal ideal domains are Noetherian. Because any ideal is generated by one element. So for instance, you can have the integers or our polynomial ring in one variable over field. Okay, so this is the, or yeah. Okay, actually we know polynomial ring infinitely many variables is also Noetherian. Okay, we proved it via Grabner basis. So this we also. However, if I would take an infinite number of variables, okay, not finite, then it's not Noetherian. So this would be an example of a non, you check yourself. I mean it's trivial. Just take the ideal generated by the first n elements. It's strictly contained in the ideal generated by the first n plus 1 and so on. So you build an infinite ascending chain of ideals which never ends. Okay. Or I mean, actually maybe I mean, if you do functional analysis and so, maybe you look at the algebra of continuous functions on something, say on an interval, compact space, or whatever what you like. These rings are not Noetherian. Easy to check. We have a compact space, ring of continuous functions on it is not Noetherian unless, I mean, unless the set is finite. Okay, so you will not meet this Noetherianity condition in functional analysis somehow. So it's something that we have here. Okay, right. What? Okay, something else. Okay, another. It's very cheap. The corollary 6.5. I can do it. It's very simple. So and very useful. So let's say A is an Noetherian ring, and M is a finitely generated A module. Then M is Noetherian. So the module is finally generated over the base ring. The base ring is a nice one, is Noetherian, then the module will be Noetherian. And the proof is so simple. We just use our corollary 6 sphere to see that A to the n, meaning that n-fold direct sum of A is Noetherian. This is a Noetherian A module. Okay, it's just because A as an, okay, A is Noetherian. Now you have this sum. It's a Noetherian A module. Now, if M is finally degenerated, it's a homomorphic image. So M is homomorphic image of sum A to the n. Okay, n will be the number of generators that you need. And now we apply the proposition. The one with the exact sequence is the proposition 6.3, which says homomorphic images of Noetherian modules are Noetherian. Okay, got it. Right. Okay, very good. Can I go for 1-2 minutes more or? Yeah. No serious complaints. We discussed about the exams. Okay, there is not so much. So let's talk a little bit about Noetherian rings. So I want to show homomorphic images of Noetherian rings are Noetherian. Oh, actually, this we know already. Localizations of Noetherian rings are Noetherian. Okay, so there is this, I can state it. This is proposition 7.1 in Nathia-MacDonald. If A is Noetherian ring, and I have a surjective homomorphism, surjective ring morphism, then B is Noetherian. Noetherian ring. Okay, I don't know, do we need to prove something here? I don't think so, because, okay, this phi will also be, if you think of A modules, it will be a ring homomorphism, but maybe if you don't like this, I mean, directly, let's do it directly. So let's say I have an ascending chain of ideals. Ideals of B. Then I take inverse images. These are ideals of A. Now I need a little bit more space. Good. So then, because A is Noetherian, there is some index that gets stationary. Okay, my pencil is almost empty. Time to stop soon. And now I use phi surjective, actually as before, and I get this. Okay, and I'm done. So actually this proof we had basically. Okay. So, okay, so the plan is finish this Noetherianity stuff. I mean, it's a finiteness condition, but then next week, I have one more week left. I want to prove a theorem which is quite important. It's about the primary decomposition. So you know that every prime number can be factored into, every integer can be written as a product of prime numbers. Okay, and now the question is, can we have such a thing in rings? I have an ideal. Can I write it as a product of prime ideals? Is it possible? Or product or intersection or what? And if yes, will it be unique? And the answer is this: if the ring is Noetherian, you can write every ideal as an intersection of prime ideals. That's very easy to prove. But there is also some uniqueness condition, which is a little bit more delicate. Okay, and this is, we have to look at it. That's not so simple. This is called primary decomposition. Very fundamental. Okay, that's the plan. I cannot do dimension theorem because I spend too much time on the graduate. I'm sorry for that. But somehow it's hard to, I don't know, plan. I don't know, maybe with more feedback from Marco and so without pandemic, I would have planned better, but somehow. On the other hand, it's useful to know it. So you cannot have everything. Okay. Any questions or comments? Let me maybe stop the recording.